Okay, hello everyone. My name is Natalie Brown, and I am a graduate student with Ken Brown. And today I'm going to talk about some work I've been doing studying leakage, also some work I've done with a postdoc in our group, Michael Newman. So fault tolerance really depends on how errors propagate. If we look at a surface code, and of particular interest are really bad hook errors that propagate from our Ancilla qubits to our data qubits in harmful ways. So if we look at an unrotated surface code, we know that we can measure our syndromes this way, or we can measure them this way. And either way, we're immune to these really bad fault patterns. However, if we look at a more qubit-efficient surface code, we know we have to measure our syndromes this way. If we try to measure them this way, we're going to leave ourselves very vulnerable to these dangerous fault patterns. So what about leakage errors? How do they propagate? When do they cause damage? And how can we mitigate that? But let's take a step back for a second. And what is leakage exactly? So the ideal qubit is a two-level system. And we encode our information into these two levels, so-called the computational subspace. However, this is a little bit of fantasy. In reality, the devices in which we build the qubits on are superconductors, atoms, quantum dots, and all of these things have access to higher level energy states. So when our qubit leaves our defined computational space and accesses these higher level energy states, we now no longer have a true qubit. We have an ill-defined qubit. And this is what we call a leakage error. So why is leakage bad? Well, I already told you it corrupts our qubits, but it not only corrupts the qubit it happens to, that leaked qubit can now interact with other qubits in harmful ways. In this talk, I'm going to focus on what we call undetectable leakage. So there's a few types of leakage. Erasure leakage is one of a different type of leakage. And what I mean by undetectable is that I cannot measure it. I cannot measure that higher energy state. So when leakage happens, and I try to measure a leaked qubit, I still project down into that computational space, and I can't tell whether I'm reading a leakage error or maybe something else. If you can measure that third state, you can detect this leakage. That's definitely going to help you in your error correction. But again, I'm going to focus on this undetectable problem. Leakage also renders error correction syndromes useless. And it lives on and accumulates. If your data has leaked and you don't remove it, it's going to continue on in your system, disrupting things. So you really need to move it in a very efficient manner. Fortunately, Alferis and Terhall showed that a threshold does exist in the presence of leakage if you add so-called leakage-reducing units or leakage-reducing circuits. I'm not going to talk about that a lot in this talk. There's some very nice work by Sukkar, Cross, and Gambetta where they look at the overhead of these different devices and their effectiveness. But most leakage-reducing circuits are based on either a swap gate or some type of teleportation scheme. In this talk, all of the data I'm going to show you has implemented this swap gate. And how it works is if your data has leaked at the end of your cycle, you swap roles with your Ancilla, and now you measure that leaked data qubit. And then the next round, that data qubit is your Ancilla, and you keep swapping them back and forth. So in this way, leakage is only able to live at most 2 rounds of syndrome extraction. And then hopefully what I hope to express to you in this talk is that it's hard to model, and how you model it is going to greatly affect the fault tolerance of your system. So what are our ingredients for fault tolerance? Well, these 3 really work together in a meaningful way to get you fault tolerance. So what I mean when I say leakage interaction model, I mean when a leaked qubit and an unleaked qubit go through a 2-qubit gate, what happens to that unleaked qubit? And we'll discuss a few of those. Your physical system can influence your leakage interaction model. what's the physical structure of your qubits, and how are you doing your gate, and how does that cause leakage? It's going to seem like I talk about these two things separately, but it's actually very hard to separate the two. They really go hand in hand. And then how does this all play into the fault tolerance of your quantum error correction code? So first I'm going to talk about different leakage interaction models. So I hope that this is pretty easy to see, but I know some of the fonts have been small. But there's kind of three regimes that leakage interaction models fall under. So this picture, it says leaked under here. I'm talking about a leaked qubit, and then an unleaked qubit, and they go through a gate. What could happen? Well, the worst case scenario that in our lab we like to refer to as the nightmare model is that if a leaked qubit goes through this 2-qubit gate, the unleaked qubit now becomes leaked. This is a little scary for us, so I'm going to leave it to the experts. The next talk is all about this model. I'm going to focus on the bottom two. The standard leakage interaction model is your leaked qubit interacts with your unleaked qubit, and due to that interaction, the unleaked qubit incurs some kind of error. Now, that error is not a leakage error, but it's some kind of error. And then perhaps a better model, which we'll also talk about, is your leaked qubit does not interact with your unleaked qubit, but maybe this unleaked qubit somehow gets an error anyway because of how you do your gate. So first I want to talk about this interacting leakage model. And we call it our depolarizing leakage model, and it has been studied by Fowler, it's been studied by Sucara, Cross, and Gambetta. And in this model, if your leaked qubit is on your control or on your target, it does not matter. The other qubit undergoes this depolarizing noise channel. Those lines are really wavy now, huh? So Fowler studied this model, and on the left here, he considered just no leakage, just gate depolarizing noise. And we see that our logical error rate scales as it should. It scales correctly with the distance. And then on the right here, he considered a leakage rate of about 1/10 the probability of the depolarizing noise, gate noise. And you see that the distances now scale differently. And we see this kind of distance drop where our distance 3 codes are now behaving like distance 1 codes. Our distance 5 codes are now behaving like distance 3 codes. So Suchar, Cross, and Gambetta also looked at this model, and they studied not only different leakage reduction techniques, they also looked at how different decoders could help you. And then I got interested in this model when we were looking at 2 different types of ion-trapped qubits. A hyperfine qubit, which can leak, but has very low dephasing noise, and a Zeeman qubit, which has very high dephasing noise, but does not leak. So these black lines here represent my hyperfine or leaky qubit, and these red lines here are my Zeeman qubit or my non-leaky qubit. And you really see here if our dephasing noise and our non-leaky qubit can be suppressed, then we see an improvement over this hyperfine qubit. And this really shows this distance damaging fault that this depolarizing leakage model has. And you can see that here by this red line, which is a distance 3 surface code, and this black line here, which is a distance 5 surface code. They're behaving the same way. So, and here you see a distance 5 surface code, and this distance 7 surface code is almost on top of it. So again, depolarizing leakage causes this logical error that affects your code's distance. So what exactly causes this distance drop? And before I go into that, I want to take a little second and talk about how this swap gate works in a little bit more detail. So in my syndrome extraction cycle, I have 4 C-naughts, and then I'm going to add a swap on the end. And due to gate cancellation, that amounts to adding 1 extra C-naught at the end of this cycle. And so my first round, my Ancilla are my black dots, and my data are my white dots. And the next round, they're going to swap. So you see the qubits themselves don't move, but my stabilizers are kind of shifting up and down. So round 2 now, my white dots are my Ancilla, and my black dots are my data. And again, in this way, if a qubit has leaked, it gets removed, it gets measured and reset every other round. So what happens if a leakage error occurs after our first CNOT gate? Well, it's completely reasonable within our depolarizing noise model, leakage model, that after the second CNOT gate, it propagates an X error to the qubit on the left. And then after the third CNOT gate, it propagates another X error to the qubit on the right. And let's say that last swap gate, nothing happens. Okay? So this kind of looks like a magic trick, because you see the leakage doesn't move, it becomes a data qubit. But for some reason, these X errors propagate onto what were Ancilla qubits that now become data qubits. And this is a little bit difficult to see, but if you consider this X error here, which is here, he's now going to swap with an X-type stabilizer. And I have a little cheat sheet here. So you can imagine this X error is right here, and he's going to go through this swap. And he is going to spread this X error, which is going to come back to him and become an identity, but that X error he spread is going to remain. So that is how this kind of magic trick happens. And these X errors that were on data now get propagated to these Ancilla that now become data. So then when we measure our syndromes, these two syndromes get flipped, and our minimum weight perfect matching algorithm is going to decide that we should fix this qubit, which is then going to cause a logical error. So motivated by first looking at kind of these qubits that don't leak versus these qubits that do leak, I started to get interested in how you could mix them in meaningful ways to help mitigate leakage errors. And that kind of naturally led to, well, which is the worst error? Is it better if your Ancilla leaks? Because if your Ancilla leaks, Ancilla gets reset every round, so I don't have to do any type of leakage reduction. Or is it better if your data leaks? But if data leaks, that's fundamentally bad, so you have to remove it from the system. So you have to do some sort of LRC, which means you add extra gates, which means you add extra fault locations. And the answer to this question actually turned out to be kind of interesting. So I looked at just a toy model where I considered, again, my data leaks, my Ancilla does not, but because my data leaks, I have to implement some sort of LRC. And then a toy model where only my Ancilla leaks, and since only my Ancilla leaks, I don't actually even want to use an LRC, because this swap LRC will just allow leakage to live longer. And it turns out, as you can, the graph's been up here for a minute now, one scales correctly, and the other one exhibits this distance drop. And so this is interesting evidence that this damaging leakage error is coming from leakage on the Ancilla. And so we can do this for higher level distances. And now if, again, we look at this distance, now 5 Ancilla leakage line, we see that the slope is parallel to this distance 3 data leakage line. And again, for distance 7, we see the distance 7 Ancilla leakage line is running parallel with our distance 5 data leakage line. So this is interesting, but again, this was just a toy model. So how can we see this in practice? Well, talking to some folks at IBM, I came to the understanding that maybe leakage in the cross-resonant gate is dominated by leakage on the target. And I was very happy when this paper came out by this group at UC Riverside, because they did a error budget for the cross-resonant gate, and they really justified that your leakage errors in the CR gate are dominated by leakage on your control qubit. I think I might have said target earlier, but it's leakage on your control. Okay, so how can we use this? Well, we know through this gate identity that we can add some Hadamards and flip the direction of our gate. And so that motivates kind of this gate bias model, where we flip the direction of all our C0 gates so that we can take advantage of this and point the leakage onto the data qubits. Now already, this is better than just the standard model where we naively don't do anything, because in this model, leakage only lives one round. We point the leakage on the data, and then we swap it at the end, and it gets reset, and those qubits become Ancilla. So we modeled this, and again, the standard model is just, we don't add any single qubit gates, we just, we don't do anything. Again, it's this circuit right here. And then the gate bias model is we add 14 single qubit gates, which have also error associated with them. And we see, again, by doing this, we get back the scaling that we desire. And you can see that very clearly here on our distance 7 standard model is almost on top of this distance 5 gate bias model. Okay, and now how about how your physical system can influence maybe your leakage interaction model? So Ken really likes ions, and so we study ions a lot in our group, and the Mølmer-Sørensen gate is a way of implementing a C0 gate in an ion trap system. And when you do a Mølmer-Sørensen gate and one of your qubits has leaked, this XX 2-qubit interaction does not happen. But you don't know that it does not happen, so you're still going to apply these single qubit gates. And so that prompted us to do a polytwirl approximation and come up with this MS leakage model, where if you leak on your target, we apply E phase to the control qubit. And if we leak on the control, we apply E bit to the target qubit. So now let's look at how this new leakage interaction model, what happens to that error that was so bad we talked about earlier. So in this new model, leakage is only going to spread Z's. And so instead of spreading these bad X's, we spread a Z to the qubit on the left, Z to the qubit on the right. And now, these Z's are going to propagate in such a way that we're never going to have this bad distance damaging fault. We're always going to be able to get a correctable error. So again, we can go back and look at our toy model and compare data leakage versus Ancilla leakage. And we see that there's not a huge difference anymore. They both scale as they should. It's interesting to see, though, too, because, again, I want to emphasize this circuit has an extra gate, so extra fault locations, that data leakage is still a little bit better. So already, when we modify our leakage model to kind of better reflect the physics of our system, we see that our fault tolerance is maintained. So this was the picture I kind of showed earlier where I was considering these leaky qubits, and under depolarizing noise, they have this distance drop. But if I now model that same thing with this MS leakage model that hopefully captures the physics of the system a little bit better, we see that our effective distance is maintained. And so maybe leakage wasn't as bad as we thought it was before. This also can motivate us to consider designing systems that don't even need an LRC. So I modeled a system where we have ytterbium-171, which is a leaky qubit, BR Ancilla, and ytterbium-174, which is a non-leaky qubit, be our data. And in this way, we don't need to use an LRC because our data cannot leak. And we see that there could be an improvement in the logical error rate when you mix qubits over just having the pure homogeneous system. Okay, so how does all of this fit into error correcting codes? What if you don't have any of these kind of gate bias, or you can't mix qubits? How does this work? So up till now, I've been talking about subspace codes, mostly the toric code, all the toric code. And subspace codes require 4 local interactions. Bravi and Poulin and Suchar and Chauncey started looking at subsystem codes, and they require less local interactions. So how do we build a subsystem code out of a subspace code? So we're going to take the same qubits as before, and we're going to add a few more, and we're going to split up what were weight 4 stabilizers into weight 6 stabilizers that are split into 2 weight 3 gauges. So now, instead of having these 4 local interactions, we now only have 3. So Bravi showed under just depolarizing gate noise, no leakage, since we have more syndrome information in a subspace code, we're always going to do better than the subsystem code. Again, those 4 local interactions tell you you have more checks locally, so you're going to be able to do better than if you have less checks. But now if you consider leakage, those less checks actually help mitigate the damage that leakage can cause. So we see that under depolarizing leakage, subsystem codes actually do much better than subspace codes. And if you consider leakage like fake news, if you spread fake news to 4 different people, that's going to cause a lot more damage than if you just spread it to 2 or 3. So that's sort of how this works. But these codes are not necessarily the most qubit efficient. So we wanted to look at more qubit efficient rotated codes. And as I kind of said in the beginning of my talk, when you rotate these codes now, you leave yourself more vulnerable to bad fault patterns. And so these codes, rotated subspace and subsystem codes, are not going to be fault tolerant under a depolarizing leakage model. However, we can look at them under a leakage model with more structure, like the MS leakage model. And again, we see the same thing, that in the model with no leakage and depolarizing gate noise, subspace codes will do better than subsystem codes. They have more checks, they have more information. But with leakage now, subsystem codes outperform subspace codes, again, because they're able to mitigate the effects of leakage. Now, what's a little misleading here is that these 2 codes have a different number of qubits. And so we wanted to compare a subspace and a subsystem code that had the same number of data qubits. And so we also looked at Bacon-Shor codes. And you can see Bacon-Shor codes do much better than rotated subspace codes at smaller distances. When you go to higher distances, there's less than an improvement, and this is because Bacon-Shor codes do not have a threshold. So what are these requirements for fault tolerance? It depends on your leakage model, but if you have depolarizing leakage, then you must have both a standard and a subsystem code. No other combination will be fault tolerant, so a rotated subsystem code is not fault tolerant, or a standard subspace code is not fault tolerant. But if you're able to change your leakage model in some way, then either a standard lattice geometry or a subsystem code would work. So a rotated subsystem code is fault tolerant, or a standard subspace code is fault tolerant. And then in terms of overall qubit requirements, the most qubit efficient codes under these leakage models for depolarizing leakage is standard subsystem codes, and for MS leakage, it's rotated subsystem codes. So in conclusion, Ancilla leakage is more damaging than data leakage. This is independent of model. These asterisks are because I did not consider the nightmare model when leakage causes leakage. And fault tolerance really depends on your leakage interaction model and your choice of QE, quantum error correction code. And if you can somehow isolate your leakage events to your data qubits, then the surface code can be fault tolerant. And if you're able to change your leakage interaction model to a model where your leakage does not necessarily cause the error itself, then you're going to be able to take advantage of this in meaningful ways. Most of this work is written up in these 3 papers. This one was just published in New Journal of Physics, and it's all about the different codes I talked about. And with that, I'd like to thank Ken and Andrew Cross, and you guys. Thank you.
Well, that was a wonderfully clear talk. Thank you very much. I really like the allusion to fighting fake news, and I think if we can find a way to use quantum error correction to fight fake news, then we might really be on something. Questions? Do we have a, shall I grab a mic? Oh, here we go. Yes, please.
So for now, do you have any knowledge of whether or not the leakage error rate is dependent or not on the physical platform? Saying like if the trap ion leaks more than superconducting qubits, or the other way, maybe?
Yeah, so I think trapped ions do leak more than, okay. So right now, I think we're more worried about general gate noise. So that is probably our limiting error. So I should also say that I don't think leakage is going to be the problem for near-term experiments and implementations. But in general, the leakage rate is higher in trapped ions than it is in, say, superconducting platforms. But even if you change these rates, this is kind of, Fowler is more interested in superconducting qubits. And it's still, even at small probability of leakage errors, you still see these effects.
So is that because, is it due to the way that the CNOT gate is implemented?
Yes.
Okay.
Yep. Which is why in, say, I have too many animations in my slides. This is very nice. You can't do something like this in a trapped ion scheme because you don't have any gate bias. These things that cause leakage are going to go to any end of that CNOT gate.
Okay, I think we have some questions of it. Oh, yep, choose one.
This one might be quite quick. So just following on from that question, you just flicked back to some plots and you said you can see that leakage has an effect, and you were alluding to superconducting qubits, and I could see the depolarizing probability. What's the leakage rate here?
This plot specifically, the leakage rate is 1/10 of the depolarizing probability.
Okay.
And then just for,
is that
in
realistic
this plot, leakage rate is 1-to-1 with the 2-qubit gate probability. And again, both of those are motivated by the platforms that they're trying to simulate.
Okay, thanks.
Yeah, I think I saw another couple of hands pop up, or perhaps, yep.
Thanks for the great talk. Have you thought much about using different kinds of gadgets to measure the stabilizers to avoid these problems, like either using fault-tolerantly prepared cat state or flag error correction, something like that?
So we did look at, it's going to take me forever to flip down to the Bacon-Shor and the rotated subspace subsystem codes. We did look at using different cat states, and it really depends on what your leakage model is and what code you're looking at, but that is also in the paper.
Okay, cool, thanks.
Any other hands? So I guess a question to wrap up with is, at the beginning you identified the different kinds of scenario we might be in, whether we're going to cause depolarizing errors, or whether we just have no effect when a leaked qubit is involved in a gate. And you mentioned the nightmare scenario, which is sort of contagious leakage, I guess. Do you have any thoughts about that, tackling that, apart from listening to perhaps the next talk?
Yeah, so I'm very excited for the next talk, and I'm very excited to talk to you after the next talk. My thoughts on the nightmare model is, one, you really have to remove your leakage efficiently. So I've said here that the damage is caused from Ancilla leakage, but what I really mean is you can get a logical error in 1 round of syndrome extraction from Ancilla leakage. It's going to take 3 rounds for a data leakage to cause a logical fault if you don't remove it. Now in this case, I'm removing it. So with the nightmare model, you need to be removing that leakage a lot faster. And if you can move it onto your data and remove it from your data in at least 2 rounds and not let it propagate to that 3rd round, then you're going to be okay. But yeah, you need to remove that leakage fast.
Okay, so a kind of threshold in terms of how long it's allowed to stick there for,
Exactly.
so that it doesn't cause like more leakage to spawn.
Exactly.
Yeah. Okay, well, thank you very much. Let's thank both our speakers again.